Wow, amazing music. Marta, tell us about today.
Hello, happy Asteroid Day then.
Thank you. Thank you.
So, well, thanks for hosting us for this afternoon with our Avengers. And my name is Marta Ceccaroni. I will be co-hosting with Toby. I am a lecturer for the astrodynamics module here in Cranfield University. And co-hosting with me is Toby Thompson.
It's great to have you with us. Thanks for joining us. I can't believe we're hosting an event which is Welcome to an Afternoon with the Avengers. Yes, you did hear that right. The subtitle of this event, we're talking about our real-world planetary defense initiative. It's not often you get to be involved in something as big as that. So thank you for joining us. We want this session, the live session at least on YouTube, to be interactive. So we welcome your questions, your comments, your challenges, your observations pretty much at any time. And if you're watching the recording, there are still ways to interact with us. So stay watching and get involved, I think is the biggest thing to say. So we're on Asteroid Day. How do we come to International Asteroid Day? Where's it come from?
Well, today it is the anniversary of Tunguska, which was the first recorded event on the history of humans. It was 1908. It was in Siberia. And where this asteroid arrived on Earth, and there were 60 billion trees just smashed to the ground because of the air blast.
This was an air blast. It didn't hit the ground.
Yes, it was just the air blast. The meteorite was never found. It exploded 10 kilometers from the ground.
Wow.
It interested a zone that was pretty much like Greater London, a bit more, so 2,000 kilometers square, pretty much. And it was such a big thing that in London, it was midnight, so it was early morning in Siberia, but it was early morning in London. And you could see, well, this is a picture from the Greenwich Observatory, and you could see, even if it was midnight, you could read newspaper. There are kind of testimony, the people that are testifying it. You could read a newspaper without turning the lights or any artificial light on.
And that's a picture of Greenwich National Maritime
College. The exact moment, yes, wow. Of the light of Tunguska. So
that's incredible.
Yes, that's it. So events like these pretty much happen once per century, then.
Wait a minute, we're due one pretty soon.
Well, we are not due one. It's probability thing, so it might happen, but it's, statistically they happen pretty much once per century.
And we don't want it to happen, I take it.
Well, we need to predict that and to be aware that no one is going to get hurt, and that's why planetary defense.
Let's
we'll
hope.
talk about it today. So. These are asteroids, which are essentially rocks and remainings of the materials with which the planets were formed 4.5 billion years ago.
So from what size to how big? How small to how big?
Well, it's like when you break a vase. It could be big ones, very small ones. There is Ceres, that is the biggest one, and is more of a dwarf planet than an asteroid. And then there is dust and every sort of size really.
So is a dust particle, is that an asteroid?
Yes, it's part of space material, so yes, it can be an asteroid. So essentially they are the planet, the remaining part of the planets that didn't form another planet stays around orbiting the Earth, orbiting the Sun, mostly between Mars and Jupiter.
The asteroid belt.
Yes, exactly. But sometimes they come close to the Earth. They might hang around pretty close, like Apophis that we will talk about in maybe another event that is coming about in 2029, very close to Earth. Or they might even impact. So like the Chelyabinsk event that we might have seen a few years ago happening. And
look at that.
yes,
That's
was
incredible.
Again in Russia in the morning. There are lots of video because the dashcam were checking it, so it was very well recorded. And essentially it was very early morning, and the light was 10 times brighter than the sun, the light that came out, so it was pretty huge. And this is the guy when they got it back So this is the meteorite. So once an asteroid arrives on Earth, it's called a meteorite.
So a meter and a half by 2 meters, maybe?
Yes, it's a 500 kilos fragment. This is the biggest fragment, and we've got a small fragment.
Yeah, we got some in the studio. Can you believe it?
So obviously, as soon as a meteorite comes on Earth, there is a kind of meteorite hunting search for the fragments that are on Earth. So that is one that, that was found.
So the fragment that we've got, and hopefully we can cut to that shortly, you've bought that. That's something.
Yes.
You've not found it. You've not gone
No,
to Micheli
no,
bins and found
unfortunately
it.
not. I'm not a meteorite hunter, but
so
you can
who
buy them.
owns? And ownership seems really strange or something like that, but someone owns that.
Well, I think the founder owns it, and that's pretty much it.
In someone's garden
yes,
somewhere.
very often they are in going to institutes and for people to find it. And
Incredible.
And so
We've got a close up now. Which one is it? Just point
this
out
one,
again.
This one. This is
Okay.
Chelyabinsk.
And it's black on the outside because that's the.
It got burned for the re-entry, so that is the crust, and it's burned for the re-entry part.
And do we know what that's made of? Can you?
Chelyabinsk, no, I don't remember the. Well, I think it's just silicate, not much more than that. So it's usually it's either metal or silicate. The most of the asteroids are of these two materials.
I still can't believe I'm just a few feet away from an asteroid or a fragment of an asteroid here.
Yes.
But I guess we're all star stuff, so I shouldn't be too surprised.
Yes. Well, they are rocks essentially, but they've got lots of history because they remain pretty much pristine from the beginning of the solar system. So we can have a hint of what happened at the very early stages of the solar system.
So more than 4.5 billion years old.
Yes, yes.
Quite a lot more than that by the sound of it.
Well, that is when they formed, and the material were formed even before. So.
Incredible, incredible.
So anyway, they come as close to the Earth as you want. And for example, there is the very famous example that got the dinosaurs extinct.
And Chicxulub.
Yes. Do you want to end up like a dinosaur and get extinct? Then we need some planetary defense. And that's exactly what is the job of our planetary defenders that we will see today. So we've got, anytime you have a danger, what you do is nothing but you have to observe it, and then you have to characterize the risk, and then you have to mitigate and communicate to the public whatever it is. And we will have our guests today that are exactly doing this part of the planetary defense.
So who have we got joining us today?
We've got Ettore Perozzi, former head of the Space Situation Awareness Office at the Italian Space Agency. Marco Micheli, astronomer and NEO observer at ESA NEO Coordination Center. Federica Spoto, astronomer at the Minor Planet Center. And then Marco Fenucci, mathematician, NEO dynamicist at ESA NEO Coordination Center. So, hello everyone.
Thanks for joining us.
Okay. Then, so the planetary defense was then born because we were looking around for, whatever happened, and I was pretty scared. So, Ettore, were you there when planetary defense was born?
Yeah, let's try someone else. Maybe we go to Marco.
Okay, then, if the planetary defense is okay, then Marco. Sorry. So the thing is, how do we discover the asteroids nowadays, Marco? You are there with your telescope at the backyard of ESA, watching all night long the sky, or what?
Yeah, no, that's not exactly how it works anymore. It's way more complex, and it doesn't involve astronomers like me actually spending any time outside looking through a telescope. It's all, fortunately, more modern. There are telescopes all over the world that are dedicated specifically to that. They are pretty big. They are machines that they have basically almost nothing to do with the telescope you can have at home, the telescope you look through. The telescope is mounted to a digital camera, so it takes snapshot images of the sky at night, And instead of taking just one image, it takes a sequence of images. For example, one every 10 minutes in a certain spot of the sky. And that's actually important because that's the way we detect an asteroid. An asteroid in Greek means something that looks like a star. So you'd expect it to look like a star in the sky, like a little dot of light. However, contrary to a star, an asteroid moves. An asteroid is close to us, it's in the solar system, it moves around the sun, it orbits the sun. So you don't see it as a stationary star, but you see it as a moving dot. So by taking images, a sequence of images over time, over a few minutes or an hour or so, these telescopes actually do find asteroids as basically the little star that moves in the sky. We'll see a bit more about that maybe in a bit. And an astronomer like me, basically what we do is we use these telescopes to take images of the sky and chase the asteroids that we are interested in. And the really cool thing is that these things being digital systems, not things you have to look through, we can actually control telescopes that are literally all over the world. So I'm an astronomer at ESA, I'm in Italy right now, but I can use a telescope in Australia right now if I want to. I just connect and the telescope takes images of the sky for me and sends them to my computer and I look at them on my computer.
So Marco, you presume you've got a book time. You've got a book time on those telescopes, or can you just drop in?
Yeah, that's an interesting question. Yeah, in many cases you have to book time. We specifically, for our needs, we go around and ask for telescopes, to telescope observatories, to get specific high priority access to many of their telescopes, which is a bit harder to get. We have to convince them it's important because we do need the quick reaction. Contrary to many other things in astrophysics that are phenomena that happen on very long time scales, our stuff is really fast. These things are coming for us. These are really heading towards us. So we really need the quick reaction. And that's something we've done a lot here in ESA, is to set up this network of telescopes that allow us to get access whenever we need, including like within minutes of a specific need. Not easy, yeah, it takes a lot of time, but it's planetary defense, as we were saying, it's important for humanity. So it's a bit easier to convince people that, yeah, we actually really need to have them.
So you spend your days in planning whichever asteroid you think is the most important. How can you discriminate between those?
Yeah, good question. Yeah, we discriminate. We discriminate quite a bit because there's a lot of them out there and we have to choose. And the choice is actually, let's say, pretty easy. And we are a planetary defense office, so we are here to defend the Earth from impacts of asteroids. So the first cut is anything that can hit the Earth is interesting. Anything that doesn't have the orbit or trajectory to hit the Earth, well, we don't care.
Neat.
So that one already goes. Very easy. And then within the ones that have a possibility to hit the Earth, we have a sort of a ranking that depends on how large they are. Of course, the larger, the more scary they are. How probable it is that they might hit the Earth, and how distant in the future is the possible impact. And these things put together in a sort of a recipe that we have tell us the ones we care the most. The bigger, the closer the impact and the higher probability, the more we care. And with this, we prioritize and we try to choose the ones that need more monitoring.
Okay, and what is actually an observation then? So you plan it, you point the telescope, you got something back from your telescope. What is it?
Yeah, we get pictures back, as I was saying. We get a sequence of pictures. We have seen something in the background there. And
bunch of dots.
The real, yeah, bunch of dots. Yeah, here's a picture. And it doesn't look like the sky because it's reversed, it's negative. So the sky is the white background and the stars are the little black dots you see. And we're showing it in reverse, in negative, because it's easier for your eyes to see things. And this is typically images we get. And as you can see, it's actually not a single image. I hope you can see that it's actually an animation. It's looping through. And it's actually what I was saying before. The animation is made with a sequence of pictures taking a few minutes apart from each other. And somewhere in there are actually little
Don't give
dots.
Hints. Don't give hints. Because we are going to ask our public to play with us in a minute.
I must admit, I can't see it. If I'm looking for something moving across that screen, I can't see it just
so,
yet.
Essentially, you know that the asteroid is there only because, well, you gave the right time and where to point. and then you've got this image back, well, this GIF back, and then you are searching for it. So you search for a moving dot, isn't it?
Exactly. Yeah,
Okay.
exactly. Search for moving dots. A lot of it is still done by eye, and we'll see in a bit why. It's
Okay.
interesting because the human eye, or the human brain, because the eye is just the tool, but our brain that actually does the real deep thing in there is still better than any software we've written. So these telescopes that I've told you before that are dedicated to discovering asteroids, of course, at first they have some software that goes through the images and look for dots that move. But then in the end, they just show what the software thinks it planned. They show it to a human being, and it's still a human being at the end with training and with expertise and with actual biological human eyes that say, yeah, this one's really an asteroid, versus no, this one is a defect on the image, or it's some camera artifact or something. So yeah, it's still humans are still better.
It's amazing that our eyes and our brains are fitted to that. You'd think AI would be trained to see this stuff, and you could do it automatically.
They're trying. It's getting
They're
better.
starting. Yeah, they're starting. Still, Marco can beat them.
That's incredible.
Trained human is still better. We'll see how long it lasts.
So after you spot, let's say, a moving dot in a picture like this one, then you measure it somehow.
Yeah.
And
we measure where it is in the image, and basically we measure each point with respect to the stars in the background, and this tells us exactly the direction and where it is. And these measurements is what I do is what we call astrometry. It's just a sequence of positions in the sky versus time, and these points are the basic starting information that we have to compute the trajectories. Then Marco will probably tell you something more, or Federica.
Okay.
And
okay,
from
then
there on, the whole process starts.
We will ask all our audience to take a look at to be an observer, really. So when you search for a dot in here, there are 3 rules, if I'm not wrong. It has to be a moving dot, it has to move on a straight line, and it doesn't have to blink or appear or disappear. What are the things that are appearing or disappearing?
Yeah, there can be various things. The most likely is what we call cosmic rays. It's basically some particles from the sky, charged particles, for example, from our sun, that come and hit our camera and leave a little dot. Okay. They're not light, they are cosmological particles, but they do leave a trace. But since they happen once, they only leave one dot in one image. And after it's just physically there in the sky, so it will leave a dot in every image of the video. And that's why you have that rule. You have to see a dot that moves and stays there. Of course, it comes back because it's a loop.
It's a four image loop, if I remember right. So, well, how can we ask our audience to play with us?
If anyone knows the game of battleships, then I guess you recognize this. So you want people to find the
there
number
are
and the
three
letter.
asteroids in the image that we are showing. Essentially, post on the chat on the web, on the chat on YouTube, the letter and the number of where you think the asteroid is moving, all the 3 of them, and we will give the solution at the end of our event today. So the game, you can find the game at this link. The QR code will pop up during the event quite a lot of times. Then once you have the solution and you figured out the solution, then you have to post it on the event chat. So this is the link.
So is this a game or is it citizen science? Because I was involved back in the 90s with SETI, the SETI search.
Well, this is just a game where they already discovered the 3, actually 4 the asteroids that are in there, but one is too faint, so you cannot see, so it's going to be just 3. But there are programs like Catalina that are starting to involve people to actually try to spot asteroids from the images. Wow. And I can I can post the link right after in the description of the event. So it's very important if we can go for citizen science.
So get involved, I guess.
Yes.
Scan the code and get involved. Fantastic.
Absolutely.
Okay.
But still need human eyes.
Yeah. So, well, can I ask you, Marco, what was the strangest observation you have ever done?
That's been a lot. I mean, when you do a job like this, you have a lot of fascinating things that happen that you see in the sky. Personally, I'd say the most fascinating and intriguing one was, well, now 8 years ago almost. when I was doing a normal observing night with one of our ESA telescopes, and I got contacted by a colleague from the United States that I'd worked with in the past. And he asked me to sort of check out an asteroid that they found the day before. So I got some more data with our telescope. And when combining his data with my data, I realized that there was something pretty weird in that asteroid. And it's the fact that it was not moving in an orbit around the sun. It was coming from outside the solar system. So it was not an asteroid of our solar system. It was not a body of our solar system. It's what we call an interstellar object. And that moment, that realization, when I saw that and I first realized this thing is unique, this thing is the first ever, that's really exciting. And that object then became what we nowadays know as Oumuamua. There was a lot of story, a lot of attention, a lot of research around that object. And it became probably the highlight for our field for those years. Still is probably one of the coolest things that this community has found and discovered since we started observing the sky looking for asteroids.
So once you saw it, well, it was pretty fast, if I remember right.
Very fast. It was faster than a normal asteroid.
Okay, so you could observe it for a while, or it was just, well, a one shot of observation.
Yeah, that was the challenge. It's basically one shot. It's a couple of weeks basically of easy observability. Then of course it was a cool object, so we tried to use like Hubble Space Telescope and any big telescope we could get our hands on. And with Hubble, for example, we could keep an eye on it for a bit more, like a couple of months, and that was gone. That was too faint for anything we have on Earth and in space. So it was a very short, very brief boost of science. And then working on the data and trying to understand what the hell that thing was. And it was very, 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 very interesting. Wow. A lot of people wrote a lot of science, a lot of papers. It's amazing how a single observation can trigger.
And it was your observation. You're the guy.
I was part of the discovery team. It was a group of people from the US and myself here at ESA and a bunch of other people. And one thing I'd really like to point out in this community, and Martha knows it, and it's something that is really cool, is that it's a field where we collaborate a lot. Contrary to many other fields of science where everybody does its own work and finds its own science and publishes it, here we are very collaborative. Every time we discover something, every time we get some data on an asteroid, even any kind of data we get, any measurement of the position like the ones I do that I mentioned before, we don't keep them to ourselves. We publish them immediately. We post them, we send them to Federica, to the other guest, to the Minor Planet Center. And the goal of that center is specifically to make every observation of everybody available to everybody else. It's a very open community, a very collaborative field. And that happened with Oumuamua, happened with everything. We share the data, we alert each other, we use each other's facility to get data as fast as possible because it's a really fast-paced field. It's something that we really have to do.
Planetary defense, so it really makes sense. So
exactly, it has to be.
Well, thanks a lot, Marco. So, well, the thing is, it is planetary defense, so it really makes sense to have this whole thing that is global, and this coordination is pretty important. So I think.
Should we go back to Ettore?
Yes, I think so.
Yeah, let's go back to Ettore, who we tried to contact earlier on, but Ettore, I think, screen is frozen there. But Ettore, are you still there?
Yeah, I'm here. Thanks a lot.
Fantastic.
When we're talking about probability and asteroids, and that's typical issue about probability. What is the probability at exactly at the same moment in which you have to make your speech, then the line drops?
It's highly probable.
Exactly.
So, Ettore, we were talking about planetary defense. Were you there when it was born?
Yeah. Well, I'm not exactly that old, but I witnessed a lot of let's say, born and reborn, because I think that planetary defense was reborn several times. It's not only once. So I'm going to tell you some of these events. Some I witnessed by my own, some not. For example, one may ask, where was the first near-Earth object near an asteroid discovered, or somehow when we realized that there were asteroids even close to the Earth? Well, usually the starting date is 1898, when Gustav Witt and Auguste Charlois independently they found Eros, which is actually the first near-Earth object that has been found. But actually, if you read carefully From the Earth to the Moon, from Jules Verne, which was published back in 1865, so 40 years before, well, actually, Verne finds tricks in order not the capsule will never reach the moon because on their way they encounter an asteroid, and it's the first time that an asteroid, even with fantasy, has been taken out from the main belt and brought close to the Earth. So let's say Neo's first were let's say it was first a game of imagination, and then it became true in 40 years later when the first Neo was actually discovered. Then another big, let's say, another game changer somehow on neoscience happened in 1997, because that was the time when usually until that time asteroids were somehow spotted during other things, for research purposes, and people were computing their orbits and studying them. But no one really realized how large was the population and what was actually the risk. And this happened when in 1997, an object has been discovered, and then someone made computation and said, okay, this object is going maybe to impact the Earth in 2028. So, and it was published and it was said, let's say, like a normal research result. But then someone said, what? What do you mean? You mean that this is going to crash on the Earth as early as 2028? And there was a lot of fuss about it, not much about the media, but even between scientists, among scientists, it was much discussed whether a news like this, how to manage, to handle something like this. And this is where impact monitoring, conceived like a system, a regularly update, a scientific, technical, let's say, from science, it went to become an operational activity. This means to have a system that is running every day, like it's happening today. That was the time in which it was felt that we didn't need to study just one or an asteroid, one or the other asteroid, but to study them, to update their orbit, and to do it every single day and every single night. And much to the let's say, we owe this very much to Andrea Milani, was professor at the University of Pisa. And in 2 years later, he was able to build up actually a system, an object software system, that was software robot, he was calling it. That was, it's called NeoDice, and it's been the first impact monitoring system to came into operation. Then in the years to come, also JPL developed one, and then the ESA now has its own impact monitoring. But this was the time when it has been, something changed in the way in which we decided that we had to manage the asteroid hazard. So that's what it was very successful endeavor, and we discovered many Neos. Then came the first surveys that were devoted to discover asteroids. It has been named Catalina Sky Survey and Linear, which were actually devoted to find Neos. So the discovery rate climbed up. But then we realized what we have to do if we get an alert. What should we do? And we realized we didn't know who to call. I mean, the U.S. president, the Pope, we are telling to call the Pope, but it really was something that we have not. We were so much focused in computing trajectories and probabilities, we didn't realize there is a political and civil protection aspect of the whole cosmic asteroid hazard business. And this was very much realized at the very first Planetary Defense Conference. This is a very successful conference that since 2009, every 2 years, the whole community is gathering. And I remember at the first Planetary Defense Conference, someone posed this question to the audience, and the panel discussion had no answer. And that we realized we had to move on the political level. And now we know whom to call. We have the United Nations Office for Outer Space Affairs, and there are two subcommittees that are called I1, International Asteroid Network, and then SMPAG, which is for planning missions in case a hazard comes through. So now we know whom to call, and these two committees are always working. Every year they are making meetings and preparing for this possibility, so that if it happens, not only we know whom to call, but we have already experienced people that are able to face the threats. So that was another turning point in the history of planetary defense. Then I think in those years it came out. Let's call it planetary defense. That's exactly what we are doing. Then many programs started to make it to raise at the level of an agency, not only of research institutions. And ESA, for example, started in 2009 a program, Space Situational Awareness. And what happened, it was that we got an enormous boost from a funding point of view and interest from worldwide interest. When in 2013 there was this event that Marta was mentioning, that there is a little pieces even there in your studio, the Chelyabinsk event, this huge fireball, which was somehow the perfect let's say what we secretly hoped, but no one dared to say. I mean, an event which was dangerous, but not that much. No casualties, no one died. There were
but we all saw it.
People which got, sorry?
We all saw it. The whole world saw it in terms of the news.
Yeah, exactly. Again, probability, you see. Yeah, people got hurt because they got panicked, and maybe they ran out because there was a huge explosion and in the sky, and so people were not prepared. This is another good point. We started to say we should start to make exercises, and like it happens, I'm Italian. I know very well what to do when there is an earthquake, because since we go to school, we are taught on how to behave, and that's exactly what we should do, and we are actually doing. So 2013 was another turning point. We had a lot of interest and good funding, and really the programs on planetary defense programs got a real boost. Then let's make another jump. There were the first, let's say 2014, maybe Marco will agree, but in 2014, a very good telescope that is called Pan-STARRS, that was a survey telescope just for discovering not only asteroids but also other objects in the sky, other transient objects, became devoted only to NEO, and this highlighted what means to have a telescope that is doing only NEO observations. Then the discovery rate really exploded, and we reached the present rate of 3,000 asteroids per year. Please keep in mind that I remember I started to work on NEOs in 1998, and the whole NEO population when I started to work on NEOs was 1,000 objects, and now we are discovering 3,000 objects per year. So
wow.
that's how good, let's say, we all became in spotting asteroids and discovering.
How good and how scary, I guess, to a degree.
Yeah. And okay, then another point came out when also the European Union got involved and got interested in asteroids, and they started the program to focus on physical characterization. But because what we realize is that actually the danger of an asteroid is not only that it's impacting the Earth, but what is made of this asteroid. If it's a monolith metal, then even let's say a 2-3 meters object can produce a huge crater, so it's dangerous. If it's rocky, loosely bound, it would just make meteorites, and make only people happy meteorite collectors would make happy. So we need to have to yeah, exactly. And so it's the good, but it's much more difficult to understand what is made of, because you have to analyze the light that is coming from the object, not only the motion but also the light, and then try to derive from the properties of light what is an asteroid is made of. Not that easy. And then there was this project that is called NEO-ROCKS from the European Union, which started the European Union said we want to have we got to be the leaders on this issue. So started an observation program, and then let's get to the reborn of the observational activities on NEOSAR. Of course, this is the news. The big news is the starting of operations of the Vera Rubin Observatory in the US, in Chile, and it's a huge project. It will. You were talking at the beginning what kind of jump in asteroid discoveries it can produce, and at the same time, well, in Europe we have started to let's say to learn how this incredible telescope works. It's called the Fly-Eye telescope because it's like it has you see all these holes. Let's say it has 16 cameras. This means it's like to have 16 telescopes, and you're looking at the 16 telescope exactly at the same time. So it's a really new telescope, very difficult. We still don't know. We are learning how to operate, and the two will be complementary. That is, the Fly-Eye telescope will focus mostly on the imminent impactors, so the so-called asteroids that we discover, not that big, but we discover, so they are faint, and we discovered them only, let's say, weeks before they impact. So they are covering two different NEO population range. So that's the future, and that's the, let's say, the story so far.
Wow, Ettore, thank you so much. That's amazing.
Yeah. So, well, it was a long history, and we definitely see the planetary defense growing till what is today. You were mentioning you were actually mentioning. Well, thanks so much, Ettore, for your intervention. Ettore was mentioning the Vera Rubin, which is the new telescope that just came out, I think last week, started to produce data.
Surprising the world with the images.
And well, Federica was pretty busy. Our next guest was pretty busy last week exactly for that. So she was, oh my God, I have to send you the slides, but I've got all this data coming in. And well, she was indeed for that. So we were before talking about the observations, and once you spot the observation, make all the measurements and, well, all the work that Marco was doing, then they send it over to Federica. And, well, Federica, how can you know that they are not aliens?
Yeah, that's a very good question.
It's a very good question.
Also, Marta gave a very good description of what my last week was. It was exactly as she described.
Mad.
Shouting around.
Sorry, I'm late on everything, and we were handling this huge amount of data, and it was not even the beginning. So how does it work? How do you know if it's not an alien or not? It's pretty interesting from my point of view, and it involves a really huge process that goes from like receiving the observations to cleaning them to sending them out and make the community able to see. So if you're wondering what the Minor Planet Center is, the Minor Planet Center is like the single worldwide location that is supposed to receive and publish all the observations of asteroids, comets, and irregular natural satellites of major planets. So basically, if you see something that is like natural and that it moves in space, that's where you have to send your observations if you want them to be recognized. You can see two maps. One is like where we are located physically. We're in Cambridge, Massachusetts, and there was a photo of like the actual like place in which the MPC lives, like the offices are, which is the Center for Astrophysics. And we work under the auspices of the IAU. So what I really like about the Minor Planet Center is that we really serve the worldwide community. So we're there for everyone. And that's what our goal is. Like, it doesn't matter where you observe from, we always get the observations and we try and clean them, link them, and see if it is a new object, if it's not, if it's an NEO, and then we try and serve the community as fast as we can. As you can imagine, there are lots of data, and so it can be kind of tricky sometimes, but we're trying to get better and better in doing that. If you're wondering how big the MPC is, it would be nice if we had some kind of a control room like this one, but not at all. That's not how we're operating. So you can see the office on my back. That's more or less the group. There are a few people missing in that photo screenshot, but right now we're 14 people. We grew a lot in the last years, and there are also 2 job postings that have been filled recently. So it is a pretty good group. It's just like there is a lot of data that we have to handle, so there's still room for more people, but we're really happy with the group we are having right now. So how does the planetary defense works, and like what is the MPC role inside the planetary defense? Now, if you've seen Don't Look Up, the movie on Netflix, you might have noticed that a few times they mentioned Cambridge, or like why didn't they send the observations to the MPC? And also they talk about the Planetary Defense Coordination Office. So some people, sometimes we do outreach events and they're like, oh, is that real? Is that a real place? Like, do you really do that? And we're like, yeah, that's how it works. And so the Planetary Defense Coordination Office was actually created around the 1994. So the Congress, the American Congress, gave NASA some task, and the task was like, you need to discover 90% of NEOs which are larger than 1 kilometer. And so I put a XKCD type of comic on the left to give an idea why 1 kilometer was chosen. Basically because, I mean, everything that is larger is definitely bad, and we know, but also as Ettore was mentioning, the probability that it will come, they're really low, and we're pretty good at tracking them. Whereas everything that is smaller, it still needs to be discovered, but something that is around 100 meters can still have some impact, especially in the city you're living in. And so it's something that we need to track and find and characterize. And so if you're wondering what the situation is right now, we're pretty good with the large one. So more than 95% of objects have been found. We're a little bit less good with the smaller ones, till not that small to be negligible in that sense. Also, the really small one are also interesting for other scientific reasons, but the point is like we want to see it and characterize and discover as much as we can. And so that's more or less the story behind the planetary defense. NASA made this documentary that came out a few months ago, which is called Planetary Defenders. So if you want to know more also about that, you can find it on YouTube. You can just Google it, and I find it pretty cool in that sense. But so what is the role of the Minor Planet Center? It's basically in the middle of everything. So you have this big goal, which is like you search, detect, and track. Then you want to characterize and assess, where assess means you want to do impact probability. You want to understand if this object is going to impact or not. So at some point, it's been decided that we had the need of having a single place that could ingest all the observations and make them available as soon as we can for planetary defense purposes, of course, but also like to give everyone the opportunity of using asteroid data or like comet data or whatever else you might think of. And so that was our goal. How does the flow works? Again, I have a couple of like quotes from some of the movies. One is like Don't Look Up, the other one is The West Wing, because they're actually pretty accurate. So I was really impressed when I saw the TV show and there was this episode. They describe exactly what Marco was describing. It's a different telescope, but like people observe something. As Marco was mentioning, they don't send us the images, also because I wouldn't be able to see the dots, and I think I should do the game as well, because that was very difficult. And then they send it to us. And what do we do? If it's a new NEO, we put it on this page, which is called NEO confirmation page, so that people and like astronomers around the world can actually go there, get the observations, get some kind of cloud orbits to understand where the object is more or less, and try to observe it. And so they can give us confirmation, because one of our main goals is to actually define if the object is real and new or if it's not. So in that sense, we need help for the astronomer all around the world to give us observations and see how things work. And so, yeah, the same thing happened in Don't Look Up. People were asking, like, why didn't you send to the MPC? So this is like exactly as things work in a real life scenario. And a pretty big schematics, as you saw, and as I was mentioning, is basically we receive the observations, we try to understand if there can be linked to known objects, new objects, what we can do with them, and then we send them out so that we have a lot of like users that can do their independent orbit calculation, hazard assessment to try to understand if this object could impact or not. And also like this information is always public. Like everything we receive is always given to the public, except if we get some bad data. So we try and clean the catalog as much as we can, but we want to give everything to the public to be sure that they can get all the data they can use for their own science, for planetary defense, for all the different purposes. And so what about the future? It has been mentioned, the Vera Rubin, there are like other telescopes that are going to be launched soon. One is like NEO Surveyor, that's going to plan to be launched in 2027 with the goal of discovering a lot of like smaller NEOs, like 140 meters size NEOs. And the goal is like the Minor Planet Center, I like to put this because it was really mentioned in the Planetary Decadal Survey, with the sense of like the MPC, it's very important for the community to be there to collect all the data, but also like we work closely with all the astronomers, and in this case it was Rubin last week, but you know there can be a lot of different scenarios. But one of the main challenges is like how can we get ready to get all this huge amount of data. Rubin is supposed to discover 5 million new objects, which is like, this is gonna change the way in which we know the solar system, like from the asteroid point of view. And to me, it's pretty exciting. It is very, very nice to think that, you know, what we know can change and how we can move forward. And from the MPC point of view, we're really happy to help the community do that. And then, of course, we're happy to play with the data a lot.
So were you surprised by the by anything of the Vera Rubin, the quantity of data ready? Is it already producing data, right?
Yes, it is ready. It's public. There were like almost 2,000 new objects, maybe a little bit less than some have been leaked and things like that. I have to say we had to do a lot of rehearsal for this one. So we were not really, even though you always find bugs when you go live. So that was the main issue. But we knew a little bit about what type of data we were getting. A lot of them are like main belt. There were a few NEOs. It was cool to see what they can do with such a short amount of time. And so you can try and rescale. And I don't think my mind can even think about how big this is going to be. And we're getting ready. Like we have been working for that for the past 3-4 years in order to, you know, change the system. It's a big change in perspective. To show how things are going to work. And also like we need to be kind of like in the front to kind of lead the community in using this type of big data. So it's the first time that you're going to start hearing big data used close to asteroids, because usually we had really a couple of objects, few objects that you could really take care of. But now things are getting really exciting. And so I can really wait for that.
Great. Well, thanks very much for taking part to our afternoon. See you then at the question and answer later on. So, well, we've got a bunch of dots, measurements, and then there is someone that will calculate at the NEO Coordination Center and at the CNEOS at NASA. They will calculate what is the orbit, and then let's imagine that it impacts. What do? We shall call Marco Fenucci.
We need someone else who's called Marco in the session today.
So, Marco, if it impacts, what happens?
Yeah, that's what I would like to show you today. And I would like to show you what happens behind the scenes at TISA. So I've prepared a few slides that if you want to share.
Yeah, we got that.
This was an action example of what happened for real, right?
Yeah, exactly. I'm going to show you what happened on the 21st of January, 2024. And the story starts at 11:30 in the evening, because at that time, well, it was also Saturday night, and all of a sudden we receive a call on our phone, and we answer, and it's our imminent impactor system saying, wake up, there is an asteroid impacting Earth in 2 hours from now. So imagine it's a Saturday night. There were people, I don't know, looking at a movie. There were people going out at the pub and having a drink. What happened actually that night? So a Hungarian astronomer at some point in the night, he was looking at the sky and they saw a dot moving, as Marco said before. And they reported these observations at the NEOCP that Federica introduced before. And still nothing happened at that point, but after some time, Cernetsky reported more images, more measurements, and our system started computing the orbit. And with only 7 observations, the system computed a 100% probability of impact with Earth.
Oof.
And this is the message we got on our phones. And well, it said that the asteroid was small, like 1 meter in diameter. So it wouldn't cause threats, but still it will be interesting to follow it up. And also the report said that it was gonna impact somewhere in Northern Europe. So after 15 minutes, there were 100 minutes left to impact, and we started being operational. So we stopped doing whatever we were doing at that time, and went on the laptop and trying to understand what was going on. Some more observations were reported after some minutes. And at that point, the impact location was much more precise. And we computed that this asteroid was going to impact somewhere west of Berlin. So next, other 10 minutes passes, and it's midnight. And what happens at this point? Well, there were more observations from other astronomers because this object was announced on the NEOCP. And at that point, we understood that this asteroid was real. It was not some outlier like something that Marco explained before. So we started thinking about how to act. And the first thing that we wanted to do is to announce this event. So our planetary defense officer, Richard Moisel, contacted the American counterpart from NASA, Linda Johnson, and they decided to go public with the announcement. And they wrote on X, the former Twitter, that an asteroid was gonna impact in about an hour, but it was completely harmless. So they wanted to reassure also with this message that nothing was going to happen. We could just see a bright fireball in the sky. After some more minutes, after half an hour, it's half past midnight, we want to do better. So our astronomers take the lead. They are on the laptop. The telescopes are in Tenerife, in Canary Island, and they remotely control these telescopes trying to get the asteroid. So in the end, they measured 32 positions from our telescopes. And these were the only observations taken from outside continental Europe. And these were really important because they helped to better constrain the orbit of the asteroid and better constrain the location of the impact and the time of the impact. That at some point after this observation, the uncertainty was only a few seconds. So 30 minutes to impact. At this point, the asteroid enters the shade of the Earth, and it's not possible anymore to image the asteroid from the ground because it doesn't reflect anymore the sunlight. So we just need to wait at this point. But here I'm showing you how the impact location evolves as more observations are announced. So at the beginning, when we have only 7 observations, the impact uncertainty is very large. It covers a large area of Europe. But as soon as more observations arrive, this area shrinks a lot more. And on the right, you can see these red dots, which represents the observatories in Europe that were observing, that were reporting the observations of this asteroid. And at some point, you can see a red dot appearing in Tenerife, in Canary Island. And when the observation are 49, just right now, you can see that the impact location is very, very small. The uncertainty is very, very small. And these observations specifically contributed a lot to improve the orbit determination. So next, we arrived at the moment of impact. It's 1:30, and we were waiting for the impact, as you can see. I had a ferry assistant with me to watch the event. What we did was basically searching for a webcam that was pointing in the right direction that we could compute from the observations. This webcam was in Leipzig. Yeah. The webcam is in Leipzig, so a bit south of Berlin, and it was pointing north. And here you can see people in the street. It was January, so there's an ice rink in the square. And at some point, you see a bright fireball appearing in the night sky on the top right of the image. And yeah, it was very nice to see it live. And there was also a timestamp that here you cannot see, and it was exactly 1:32. That was the time that we computed for the impact. So it was very successful. We didn't stop here because people wanted to search for meteorites. And people started going hunting for these meteorites in the fields near Berlin. And we also computed where the meteorites would land on the ground. Well, we actually got the results a couple days after the fall, and people were already finding meteorites. But actually, if we compare what we computed, no, actually no. These locations were announced some days later, but our computations were really good also in this case.
Okay, and this is at the coordination center?
Yeah, this is the new coordination center during another event, which happened back in December. And that was really cool because the asteroid was discovered in our morning at 9 a.m. and it fell at 5 p.m. So it took us our whole working day, and we were following the event live. Again, we found a webcam that was pointing in the right direction, and we saw the fireball at the time that we predicted. Yeah, it was a really nice event.
Okay, that's wow. So this is exactly what happens when an impact is discovered, I guess.
Incredible.
Yeah. So I think, well, that's incredible. Yes. So I think it's time for the question and answer.
There's a few questions here in the chat.
We can recall our 4 guests all in. So if there are questions around.
Well, there's a couple of questions. And first of all, Maria says, "Way to go, Italy." Way to go, Italy, because there's a lot of Italians on the call.
Yes, that makes sense.
Yourself included. Is there a reason for Italians being interested in asteroids?
I don't know. I think it's an old school of, well, astronomers, mathematicians, and, well, the University of Pisa has done quite a lot in the orbital dynamics part, and is a kind of twin with the Neo Coordination Center. So I think it's because of that. We have a tradition of that.
Way to go, Italy. Fantastic.
And the first asteroid was discovered by an Italian, probably.
There you go. I believe Galileo was also Italian.
Yes, well.
Yeah, there you go. A few more Italian astronomers exist. And if you're watching the live YouTube, please put your comments, your challenges, your questions, your observations into the YouTube chat. Harry's got a question, and Harry, thank you for your question. How are the increased number of low Earth asteroid satellites affecting the quality of asteroid observations? Are there any techniques used to overcome this problem, or is it not significant in terms of satellites, low Earth orbit satellites? Who wants to pick up on that one first?
I think Marco Micheli. Yes.
Marco, go ahead. Yeah. Good.
It's less of a problem than for many other fields of astronomy. And the reason is that kind of goes back to what I was saying before. We take multiple images of the sky to see our asteroid move. And the fact that we take multiple images makes us in a certain sense resistant to one of them being affected by a satellite that goes through. So by the fact that we have more images and we are working on comparing them, if we see one big thing that flies through, well, we kind of know that that image is wasted, but not much more than that. So contrary to many other fields of astrophysics that, for example, spend a long time staring at the position of the sky, and if something passes through, their observation is ruined. For us, it's less of a problem than it may seem. And we've developed techniques of analyzing images, things called, for example, synthetic tracking, things like that, that do deal with that intrinsically at the level of how we analyze the data and take care of anything that is not always present in the image as, well, this is an artifact, we get rid of it. It's not as bad as it might seem.
Thank you. So Harry, come back if you want to come back on that one. There's another question here. Are observations only practical in optical wavelengths? Who can answer that one?
It's for me again, I guess.
Go on.
No, they are not. Observations to find asteroids, to spot a new one that moves in the sky, are typically today done in the optical. They would be practical in the optical and in the infrared. They would actually be a bit easier in the infrared in some cases. The problem is that the kind of wavelength regime of infrared where they would be excellent, that would be excellently suited for that, is not observable on the ground. It's only observable in space. So there have been, and there will be some satellites dedicated to discovering asteroids in space in the infrared, but it's not the most commonly used technique just because you have to go to space and that's expensive and that requires technology. The second best wavelength regime where to find asteroids is the optical. So that's why most of the Earth-based telescopes are located in the optical. However, and that's the interesting part, one thing is discovering asteroids, one thing is characterizing asteroids, meaning trying to figure out what each asteroid is made of, like compositionally, physically, how dense it is, how heavy it is, which is all very, very important for planetary defense. If an asteroid is coming towards us, we want to know what's made of. We want to know how heavy it is. We want to know the material, how it will react when entering the atmosphere. It depends on how solid or fragile the asteroid is. And in order to determine these things, they're not easy. I mean, keep in mind, the asteroid is still a little dot in the sky. So you have to try and figure out ways to know how it's made of. And this is typically done through techniques that take advantage of many different wavelength regimes. So from the optical to the radio to the infrared and millimeter waves, it's like basically almost every wavelength is used to characterize compositionally and physically what an asteroid is made of. And again, the ones that are doable from Earth are done from Earth. The others are done with space telescopes that can see wavelength regimes that are not visible from the ground.
So we're not looking at a James Webb Space Telescope use for asteroid?
We are. We are too. Not, of course, extensively. It's a very valuable resource. It's designed for general astrophysics, but we have used it. I don't know if we've mentioned before, there was an asteroid that we thought could be a potential impactor, and we worked on it a lot at the beginning of this year. And to finally know if this thing was going towards the Earth or not, and how big it was, and so on, we did ask for time. When I say we, is like the whole community, an international community of planetary defense astronomers, did ask for time to the James Webb Space Telescope. We got time. We have used two of the instruments on the telescope to observe it, and we were able to get a bunch of information that we would not have been able to get otherwise, specifically thanks to the peculiar, unique capabilities of James Webb. So yeah, we do use it every time it's really needed.
And there's one last question in the chat. This is from Kimon. So Kimon, thank you very much indeed. And I'm going to put this one to Federica. What is the coolest asteroid you've seen, Federica? And define cool.
Yeah, that's a very good question. I think they're all cool in different ways, at least to me. So when you see the impactors, for example, the cases Marco was talking about, these are pretty cool. When you start seeing your system sending you emails that is like, oh, this is going to impact, and then you can see it, and you can predict it, and you're part of the whole system. I think that's been pretty cool. Right now it's becoming more of a routine type of thing, so I thought that was cool too, because in some sense it's such a well-oiled situation that we're like, okay, it's happening again. Oh, that's nice. Let's see where it's gonna be. and then it's nice to see, all the studies that are made after, and where it's coming from, or like, and everything like that. I think Ettore also mentioned Eros. I have to say that I was reading one of Ettore's book, and I learned that Eros was discovered the day of my birthday.
Oh.
So I think this is pretty cool. It was
Congratulations.
August 13, and he has a special place in my heart for that. And I also used to work in Nice, so I feel a special connection with that asteroid. And it's also the first annual, so and that's pretty cool to me too.
And I guess everything is cool because it's at 0 degree Kelvin. Marta, question for you. Can amateurs, an average individual discover an asteroid?
Well, yes, quite a lot. Well, discover probably is more for the surveys to, well, it's more their role, but you can follow up and, well, use a telescope that if it can spot 16 magnitude and above. So a 40 centimeters telescope,
big
pretty
telescope.
much. Yeah, well, big, but
big
not
amateur
well.
telescope.
Yes, exactly. So you can register to the Minor Planet Center. Indeed, Federica will give you a code, and then you can start actually participating. So having, well, adding dots to the observation, such that the orbit is way more determined, and it becomes easier to, well, to do all the calculations and everything else. Amateurs have a huge role in this field. So not only for the observations, you can, we mentioned before that Catalina is now starting to make citizen science. You can have, if you ever spot a fireball, there are apps in which you can track the observation.
Yeah.
And it's important for the meteorite retrieval, so it's very key also, that one. And then, well, even just sharing the informations when they are the correct ones, instead of sharing the alarming news that are completely fake, that is another good role. So yes, everyone can be an Avenger indeed. So.
And what counts as a good observation? I guess it's Federica again, the Minor Planet Center. What criteria, Federica, are we using for a good observation?
Yeah, this is a very, very interesting question. We're actually working on it right now. So there are a lot of different ways you can do it. But one thing we usually consider is like the performance of the observatory over time. So once you make an observations and once you get an orbit, what you can predict is where the object is going to be in the future or where it was in the past. And so you can compute what are called residuals, which are the difference from what people observe and what we actually think, where we actually think the object is supposed to be. And these residuals gives you an idea. I mean, we're pretty like we consider like that the observations are the wrong one, and so we give them kind of a score in that sense. And so we say if the residual is small, that means that your observations are really good. We don't say our orbit is bad. We're just saying our orbit is always good. Your observations are like slightly worse. On the other side, if the residuals are pretty large, or like maybe there are some problems, and that could be due to different reasons. Like a telescope could have bad weather, but they were trying to observe anyway. It's not a performance of the observer. It's more like what was happening while you were observing in that sense. And according to how we weight, we call it these observations, then you know if the observations is good or bad. And if it's good, you add it to the fit to measure it, you recompute your orbit and make it better and better. If it's like not at the quality you expect it to be, then there is a process that automatically discards it and says we're not using that observation. Sometimes they're so far away that actually people measure something else, and we're able to tell them, we're like, hey, you thought you got that object, but you actually saw the other object, which is the same field of view, it's just on a different location. So we tell them, and we also give, we tell people and observers how they're doing and if they can improve some things and things like that.
We've got time for one more question. This is from Ipshing Fan, and Fan, it's great to see you in the chat there. Ipshing Fan is asking, how likely is the scenario for the 1998 movie Armageddon? I'm going to let you answer that one. Is that likely? Is that the Bruce Willis one?
Yes, it's the Bruce Willis one. We will talk about action and whatever means the action. So if a nuclear bomb on an asteroid is a possible thing, and spoiler alert, is not, we will talk about that actually in the second part of our event. So let's,
Brilliant.
Yeah. We're running a bit late, so we want to start, we start in 10 minutes time pretty much. But yeah, then fun. Please take a look at the second part of our meeting, and there is action to come.
So we have a 10-minute break. Thank you for sticking with us. And our guest for the first part, thank you so much for the time that you spent with us. We really appreciate it. I feel part of something much, much bigger. So thank you for sharing that information with us. For those of you watching, please stick around. We have part 2, where there's much bigger things to come, including Bruce Willis. He maybe doesn't appear in the studio, but he gets a mention. So stick around. We're going to put a timer on the screen. See you back here in 10 minutes. Thank you.
Thanks.
Possiamo salutare?
So Martha, I'm going to leave it with you to principally talk to these guys.
Yes.
You know them and you go
Should I get
Yeah,
worried
go
about the timing or?
Oh.
If you're joining us for the first time, welcome. Happy Asteroid Day. It's good to have you with us here at Cranfield University. We're talking about the afternoon with the Avengers. I can't believe I'm saying that. The subtitle of this event is Our Real-World Planetary Defense Initiative. And this is where you can get involved. We want this live session on YouTube to be interactive. If you've gotten this far on the recording of YouTube, there are plenty of ways to get in touch, not least of which is a game that we introduced earlier on in this session. So if you're watching the recording, rewind and contribute to that game. Marta, where are we in the scheme of things here?
Okay, so we have done some maths. Well, we have discovered some asteroids. We have done some maths. Are you ready for some action now?
Oh yes. Make
Okay,
it big,
then.
make it big.
Yes.
We're
Then
talking planetary here.
let's
so-
imagine that a big bloke is impacting then. What are we gonna do? Who are we gonna call? Who tells us what is, well, where is it impacting? What's gonna be the danger and everything?
This is
For
scary.
this, we've got, well, the first thing is to clear the things out. So we don't want any Bruce Willis. That is not gonna happen. There will be no nuclear bombing. There will be nothing like that because, well, is essentially we would create a shower of pieces, radioactive,
Not
all
good.
over on unpredictable orbits.
And that's not
so
good.
we really don't want that. Well, unless it is our scientific team finds that really necessary, but I don't think so.
So Bruce Willis was wrong.
Well, yes, it was a fiction. That one was pretty much of a fiction. So,
Just in case you thought it was real, that was fictional.
yes, and it would be very dangerous indeed. So anyway, we'll talk about that. Well, essentially what we have is, you might have heard that we have changed the orbit of an asteroid. This was the actual impact that we can see.
Oh wow.
So this was the linear telescope that was showing how we redirected the asteroid. That was the DART mission. It was in 2024. And well, we redirected it of, it was, well, essentially, it was like a washing machine that was impacting onto an asteroid that was a bit bigger than the London Eye.
Whoa, that's pretty big.
160 kilograms, and it was impacting at 6.6 kilometers per second. A rifle bullet is 1 kilometer per second, so
Pretty
just to have an
fast.
idea. So yes,
That's a
definitely
fast washing machine. It wasn't. Tell me, it wasn't actually a washing machine.
No. It was like a washing machine. So the size of a big one, like a laundrette one.
Yeah,
so
yeah.
a big professional one. That was pretty much the size. And yeah, it was impacting, and it could redirect the asteroid of well. This is a binary asteroid, and the period change of 33 minutes and 15 seconds, something like that. So it was pretty impressive. Well, we're going to talk of this mission and of what can we do and what is the actual damage that the asteroid can do with our next 4 Avengers of the afternoon. So let me introduce them.
Let's meet the Avengers.
Yes, we've got Andrea Pellacani, HERA GNC Technical Manager, Lorien Wheeler, Risk Assessment Lead for the Asteroid Threat Assessment Project at NASA, Detlef Koschny, that is the Chair of the Space Mission Planning Advisory Group, and Edward Baker, the Head of the UK Space Agency Planetary Defence Office. So thank you all for joining us. And then, okay, so, well, we were just saying that we have redirected some asteroid. The thing is, of that asteroid in particular, we were discovering it, well, that the period was changed in the weeks after, but then there were other updates because kind of the old rubble was getting back to the surface and giving an extra kick, and so we discovered that actually happened. So the gravity recalls back some of the grains, and that slows down even more. So there were lots of updates of things that we didn't even know that could happen in case of a redirection of an asteroid. So, and for example, there was a high school in California that was observing the sky as a lecture, and they even found out that something was not adding up with the period of time. And indeed, what happened was that they discovered that there was 1 more minute after that. Well, the deflection was of 34 minutes and not 33 as it was discovered.
This is not NASA, this is a high school.
Yes, a high school. I was telling you that everyone can be a part of the planetary defense, and indeed this was exactly that. So the more we look at the sky, the more we discover, and that is why, luckily, ESA is sending a mission to observe what we have done with the DART mission, and the mission is called the HERA mission. So, well, we've got Andrea, that is part of the team of the HERA mission. Andrea, can you tell us more about it, and what is your role in the HERA mission?
Yeah, well, I'm the technical manager of the GNC subsystem. We can consider the GNC subsystem of a mission like the intelligence, the artificial intelligence that is on board the spacecraft, which for this kind of mission is very important because it allows a little bit more of an autonomy system for the spacecraft. It's very important that the spacecraft somehow moves without any specific detailed command, because I mean we're talking about bodies that are very far away from the Earth, so there is a sort of delay for the reaction. So it's important that the spacecraft making pictures of the environment understand where it is with respect to the body, and so can move and go closer and closer, but in full safety. So yes, GMV. I work for GMV here in Spain. We did the GNC subsystem for HERA. Now HERA, as can be seen here, recently just also did a Mars flyby, gaining this extra push towards the asteroid, and in 1.5 years, so end of 2026, November 2026, HERA will arrive at the asteroid, the binary asteroid system Didymos. So as was explained before, there's been an impact. So the DART mission from NASA, but I guess that will be described later, impacted this binary asteroid system. What we need to do from ESA side is to get closer and to try to understand a little bit more of the effect of this impact. The morphology, so the bodies most likely have changed. So we need to get there with our own eyes, let's say like that, in order to understand what was really the effect of the impact, extrapolate all the data and improve the data that has been retrieved from ground. And this is the power of the Hera mission, what will, let's say, contribute to the planetary defense system, and to the assessment also of what we can do in case of an asteroid will come towards the Earth, how we can defend with this technique that is called the kinetic impactor technique.
Okay, so this is flying from 2024 and will be flying for 2 years pretty much. Well, how do you know, is your system already on? And how do you know it's going to work if it's not already on?
Yes, actually, it has been tested.
Great.
So you know that the idea is that to navigate in this binary asteroid system, where there will be a primary and a secondary body. The good thing is that we already had the binary system after launch, because we have our own Earth and the Moon. We tested it and it works very well. We also, dared to test the experimental technologies, which is the feature tracking, which is a very advanced image processing technologies, in order to recognize features on the surface and navigate according to the motion of these features. And this was tested during the flyby of Mars. So let's say it was not expected. This was something that was decided thanks to the fact that the system really showed to be very robust. And it worked fine. Of course, independently of this, that was, let's say, a chance that we took, and we are super happy to have done it. As it has been now shown in the screen, I mean, it's very important to do this kind of testing when the spacecraft is still on ground. What you're showing here is the facility that we have here at GMV. So that is a functional model of the camera taking pictures of the screen that is projecting the system, the binary system. So thanks to that, we can do a hardware in the loop, closed loop GNC testing, simulate what basically the spacecraft will finally do when it gets there. So of course we cannot go there and try to test it for the first time when we are doing the close proximity operations. This phase of testing on ground is super important, very challenging, very difficult to do, but we did it successfully. But okay, now we are also happy because we tested in flight as well. So we are confident it will work fine.
Great. So you were actually there at the launch? Wow, how
Yes,
cool is that?
That was.
That's huge.
I cannot recall. I think I have the same follow. I cannot recall something as strong as this in my entire life. First of all, so many experts in there. I mean, in there you can see Ingo Gerth from OHP, Jorge Trescantos from ISA. We're talking about really genius people that we have been sharing this mission for the last 4 or 5 years. The team was absolutely the core of this. This was a quite, let's call it a next space mission in ESA, because usually the time of development is between 8 to 10 years, 12 years. We managed to do that in 4 years. And also I can say, starting from myself, not very experienced people, because this was my first mission, but thanks to the team, this was possible, and those 3 days were amazing. I mean, all the subsystems, one after another, tested. Everything was super smooth. It was really. I remember when at the end of the 3rd day, somebody said, "Okay, LEOP session can be considered successful." I got something like, "What? Really? It flew?" It was really an amazing experience. Absolutely.
Okay, so well, the whole launch, was it early morning? Was it, or in the afternoon?
Yes, in ISOC it was 4 p.m.
Okay.
I think it was early morning in the US.
Okay.
So yes, this was the first pictures that was done, and you can see, because I mean, somebody could say, but is this really our Earth now? And yes, I mean, you can take basically the simulations of what the Earth how the Earth should appear from the. You can see the phone and the image, and then there was this. We can see this clouds formation. So it was really our Earth from space. It was really, really amazing. And this kind of images, when you see the Earth and the Moon, was used to test the autonomous navigation. So there are techniques in order to navigate for that.
So when it started, well, this was immediately after. Were you still there? So it was already taking pictures of the so fast?
the fourth day, and there was a hurry to do that because I mean you are in escape velocity. You have an escape velocity to get out of the Earth, so you really need to do it as much as possible, quick as much as possible. That's why we couldn't foresee to do this kind of testing, because the first thing that was not going very well, we should have stopped and focus on the safety of the spacecraft. But as everything was super smooth, Leo finished half of a day before, we managed to do this the fourth day after launch.
Okay, and so, well, this is the actual video for the navigation. You were mentioning the features recognition.
On Mars, exactly. So this is the Mars surface. The pictures, only 20 minutes of experiment was performed, but as you can see, all these features, a lot of features has been tracked. So the idea is basically, according to how the feature moves, I know what is the rotation velocity of Mars. I know what is my initial, let's say, guess of the state. So according to that, according how the features are moving, I can extrapolate what is the state of the spacecraft, so the spacecraft can know, okay, this is my current position with respect to the body.
And in those 20 minutes, you were already navigating autonomously, or it was just a simulation of it?
Let's say that ESOC didn't trust us 100%, so it was still ground-based guidance. So the attitude was fully controlled by ground.
Okay.
However, the autonomous solution was there, was downloaded in telemetry, and it was proven to be a good solution. So if we would have trusted, let's say, the spacecraft, yeah, it would have been good. But okay, we'll have time, 6 months in the close proximity to do that.
Wow, that's so. The next thing after this flyby is going to be really arriving to the asteroid. That is the next time in which you're turned on, and then it's definitive. So it starts.
Exactly. After the first 2-3 weeks, it will be ground based. So like Rosetta was navigating several years ago, it will be ground based. Everything will be decided by ground. But then we will trust the spacecraft to start pointing where it has to point. And after very soon in the mission, if everything goes fine, the spacecraft will also decide the maneuver that has to do. So ground will decide what should be the arc that because we will not be an entire orbit, it will be hyperbolic arcs around the body. Ground will decide what should be the shape, but definitely the spacecraft will decide what will be the real maneuver because that is the one that is the best optimized according to what the spacecraft see in the camera, basically.
Wow. Are you gonna sleep in those days? Will you be able to?
Let's say that I will be worried to disappear if there are problems on that. So I have to be there on with the luggage disappearing from the world if we have issues. But no, I think there will be super exciting moments. It will be critical because, of course, there are autonomous systems like the collision avoidance maneuver in which if there is something wrong, what the spacecraft will do is to get out, to be in a safe, let's say, position. So we have to be careful about not triggering these systems, otherwise we will lose a lot of time. So it will be very, very challenging to do it. But I think that we gain quite a good confidence. We have 6 months of time. So I think it will be exciting for sure.
Well, yes, but I really think it's actually already a success because every time you're challenging, you're trying to get something more. So the autonomous navigation is something that is not recent, but every time you adapt on that, so it's already a success, whatever happens. So you won't be able to hide. It's too much of a success already. So. Well, thanks very much. It should be, well, it's incredibly cool to have some payload on board that is designed by you. That's, well, I cannot even imagine that. So thanks for coming up this afternoon with us.
Stick around. We've got some questions for you, so stick around.
Okay, so we just learned that we can do something.
Amazing.
And we can take a look at what we can do because we have really to understand exactly what happens once we do this kind of intervention. But the problem is that we first have to understand if we want to intervene on the spacecraft, and to do that, on the asteroid, obviously. And to do that, the only thing that we have to do is to understand how much damage it could be on Earth. So how dangerous it would be, and well, what could happen. And for
what
this,
could possibly happen?
What could possibly happen? Yes. And for this, we've got Lorien that she will tell us all about the possible damages of the asteroid.
Thank you, Marta. Can I have my slides up, please?
They should be up in a moment.
There we go.
Yes.
All right, great. All right, so thank you. My name is Lorien Wheeler, and I'm the risk assessment lead for the Asteroid Threat Assessment Project at NASA Ames Research Center. And what our group does is we develop models of asteroid impact, damage, and risk to help guide planning for asteroid threat detection, mitigation, or emergency response. So today I'm going to give you just a quick overview of what's involved in asteroid impact risk assessment, and I'll show a quick example of some risk results for a hypothetical impact scenario. Next. All right, so first, just a quick primer on the types of damage that asteroids can cause. Asteroids can cause damage either by disrupting explosively in the atmosphere or by impacting the surface. The main types of hazards from either of these events include powerful blast waves, thermal fireballs, tsunami from the larger ocean impacts, or possibly even catastrophic global climatic effects from the largest impacts. For most asteroid sizes that we expect to hit us at any point, blast damage is usually the greatest hazard, both in terms of the size and severity of the damage and also the likelihood of it occurring. Next. All right, so one of the fundamental challenges in evaluating the potential damage from an asteroid impact is that there are very large uncertainties and also very little direct data across all of the aspects of the problem. These include the asteroid's properties, if and where it could even hit Earth, how different types of asteroid bodies may break up in the atmosphere, and how much damage those events may ultimately cause. So to address this, risk assessment considers both the severity and the relative likelihood of the range of potential consequences. So not just one instance of what could happen, but the range of possible outcomes and how likely those different possibilities are, given our current knowledge of all the factors at hand. Next. So when a potential impact threat is first discovered, we really generally know very little about the object. We would like to imagine that we could observe something like this beautifully detailed picture of asteroid Bennu, which we see on the left here, which was taken by the OSIRIS-REx mission. But what we really get in the beginning is more like the telescope image on the right, a tiny little pinprick of light with an estimated brightness, a distance, and some orbital motion. So everything else we have to infer based on our limited data about the broad range of possible asteroid types. Next. All of these uncertainties end up affecting how much damage we think the asteroid could do if it hits Earth. So this picture here shows the cascade of how these uncertainty ranges grow from our initial measurement down to our final damage ranges. So each potential value in one layer adds a range of possible values in the next layer, and so on. So for example, when you combine the possible asteroid sizes with the possible densities, which could range from loosely bound rubble piles to very dense iron types, you could end up with an enormous range of potential mass and impact energy. Likewise, unknown composition or structure make it uncertain how readily this asteroid might break up in the atmosphere and whether it might airburst or impact the ground. Next. So some of these uncertainties can shift or shrink as we gain data from a space mission or remote observation. Next. But other factors such as the asteroid's structure, details about its shape or entry behavior, or inherent uncertainties in the damage modeling may remain unknown up through a potential impact. Next. All right, so to assess the impact threat in the face of all these uncertainties, we have a probabilistic asteroid impact risk model, which runs millions of impact cases covering the range of possible asteroid properties and entry factors. So the asteroid properties are based on current knowledge of general asteroid characteristics, combined with any observations we may have for a specific object. So these properties are then combined with potential impact locations from orbital modeling, and then each of those cases get modeled, including the atmospheric entry, the resulting damage, and for each potential hazard that we look at. And then the results of all these cases are combined to determine the likelihood of different damage sizes and severities, how many people could be affected, and what regions could potentially be at risk. Next. All right, so to give you an example, we'll take a quick look at some risk results from a recent hypothetical asteroid impact exercise that was performed for the 2025 Planetary Defense Conference. Hypothetical exercises like these are they use a fictitious but realistic asteroid threat scenario to test and develop planetary defense capabilities and response processes. And you can check out the details of this exercise and a number of other previous exercises on the CNEOS website link that's shown on this website. But as a summary, the PDC exercise presented a threat from an asteroid that was initially estimated to be around 50 to 280 meters across, with just a small chance of impacting Earth. So the map on the right here shows the corridor of potential impact locations across the globe, colored by the average number of people that could be affected by the damage there. So you can see that there is a huge range in the potential outcomes. The asteroid is small enough that remote ocean impacts may cause little direct damage, but big enough that devastating blast damage could affect millions of people if it occurred in a high population region. So as more observations refine the orbital uncertainty, the length of this corridor would shrink if an Earth impact was confirmed, or it could move off the Earth entirely. Next. All right, so one of the first things we can look at from our damage modeling is what regions may be at risk from the impact. These damage risk maps show the regions that could potentially be at risk to ground damage, given the ranges of impact sizes and locations across all of the potential cases modeled. So the black line in the middle gives the border of where the impact could occur, and then the shaded regions show how far damage could extend around those points if it was on the larger size of estimated ranges. Next. And we can also look at more specific examples of how large and how severe the potential range of damage could be. These types of maps show a likely median blast damage size and a larger 95th percentile damage size at one example location. For this scenario, the blast damage severities could reach unsurvivable devastation near the airburst, which would flatten all types of structures, extending to larger areas of lesser structural damage, fires, shattered windows, that sort of thing. So in this case, the likely or mid-sized damage cases, they're big enough to span multiple metropolitan areas, and larger sizes could span even larger regions. Next. All right, but since we don't yet know where it could hit in a scenario like this, one way to consider the level of risk overall is to look at the likelihoods of how many people the damage could affect across all of the potential impactor sizes and locations. So the histogram on the left shows the relative likelihood of damage affecting each population range, broken down by factors of 10. So we can see that either no damage or very large damage are both fairly likely. So to help get away from this conundrum, we can also think about the risk levels in terms of the total chance of damage exceeding certain thresholds. So the table on the right gives the cumulative chance of damage affecting at least the given number of people or more. So you can think of the risk in more of a threshold exceedance sort of way. But the main takeaway point from all of this is that broad risk uncertainties like these are very typical for asteroid impact threats, and they pose a significant challenge for decision makers who need to weigh the substantial costs and risks of various response actions. Next. All right, so these large uncertainties in the potential outcomes are also why it's critical to consider the impact risk ranges and probabilities when considering response decisions, rather than just relying on single estimates, maybe on nominal properties or nominal assumptions. So these types of risk results can help support multiple aspects of response planning. Damage estimates are used in international asteroid warning network notifications of impact threats. The risk probabilities can be used to gauge what level of response is warranted overall. Asteroid property ranges and outcome risks can be used in mitigation mission design. And the damage size probabilities can be used for scoping emergency and disaster response planning. So I'll leave it there, and I hope that gives you a sense of what's involved in looking at asteroid impact threats. Thanks.
Wow. So, well, I cannot even imagine how hard it is to try to give numbers onto these things, because obviously there is, well, first of all, the uncertainty, but then also every territory has got its own properties and everything else. So it must be a nightmare to really put numbers onto that. But obviously someone has to do it. So thanks, Lorraine, for doing it. Thank you as an Avenger. So we've done kind of the easy bit. We have the
That's the easy bit?
That's the scientific part, is the easy bit.
Really?
Is observing and then characterizing, understanding the orbit and everything else. Who's gonna talk with the decision maker? That's the hard part.
Yes.
Seriously. Have we got any volunteers? Maybe Detlef?
I think Detlef has got his name on it.
Yes. Are you able to talk with the decision makers and tell them what to do, advise them? What is your role indeed?
I think advice is the correct term, yes. Let me summarize how we actually work in case we had a real impact threat. There is a mechanism available. It's different than in the movies. It's not that we keep things secret or some scientist talks directly to her president, but it looks a bit different. And I brought a slide here, which I can show. We have two groups. One is the one here on my left. It's called International Asteroid Warning Network. And the one which I'm chairing on behalf of the European Space Agency is the so-called Space Mission Planning Advisory Group. These two groups were set up about 10 years ago, a bit over 10 years ago, after many years of thinking about how to best react to an asteroid impact threat on an international level. What are the tasks? The International Asteroid Warning Network is a network where, for example, Lorien is definitely part of it. The people we heard in the first part are part of it, the observers, those that compute orbits. It's a network, and they together, in the end, if they find out there is a chance for an asteroid to possibly impact, they will have to put out a so-called notification. Not in every case, but in the threshold, which is listed up here. If the impact probability is larger than 1%, then we will receive a notification. And this has happened once. I'll come to that in a minute. If the object is larger than 50 meters, roughly in size, then this group here, the Space Mission Planning Advisory Group, will become active. And that's basically a group of only space agencies or space offices. So it's not everybody, it's only groups which have the potential of doing something in space against the object. So not Bruce Willis, but real space agencies will propose what can be done. And in this group, if there is an impact possibility, we discuss what to do. And then the important term is we advise the decision makers. So these groups cannot take decisions. These are just expert groups. And they come up with a proposal where then heads of space agencies or members of the ministries of finance, ministries of economics, typically, we inform them and they then can decide what they want to do.
Okay.
There's
and it has
one
happened this year, early this year, isn't it?
It
Well, actually,
happened-
it was at the end of 2024. So there was an asteroid, 2024 WIRE4, that made it to the news. It was the 27th of December 2024. The Atlas telescope in Chile discovered an asteroid with a non-zero probability of impact in December 2032. So kind of 8 years time from the discovery to when it was supposed to impact. It was 50 meters pretty much, so significant local damage, but still significant. A few days after, it went through the threshold of the 1% probability of impact. It arrived to 3.1 probability of impact. Then in February 2025, it was declared safe. So, but meanwhile, all the SMPAG and IU1 machines were turned on, and they started issuing all the scientific recommendations that they could. And then there is still a possibility of 4.3% to impact the moon. We will only be able to reobserve it in 2028, but then this is pretty much what we have. So Detlef, where were you when it was discovered?
Oh, that was before Christmas. I don't remember. It's too long ago. So,
But you started the old SMPAG immediately, I guess.
what I do remember is when it's approached the 1% impact probability, of course, I mean, these things don't go unnoticed. There were people contacting me saying, do you know that this object could reach 1%? So I contacted the groups that do the orbit computations, and then we really closely followed the evolution. So even before it reached 1% impact probability, we knew that something might happen. I prepared the heads of the delegations for the Space Mission Planning Advisory Group. And then when really the 1% threshold was reached, IWAN, this International Asteroid Warning Network, put a notification on their webpage, and I was informed about that. And I immediately organized a teleconference with these heads of delegations where we discussed what we should be doing. It turned out in this particular case, we basically concluded that we can do some studies on low level, but the expectation is, of course, 1% is not very much. It means 99% it will miss. And we basically agreed that we will follow the evolution of the impact probability for a bit more until we are really sure that it's dangerous. Okay, and about a month later, it turned out, no, the impact probability went basically down to 0. But some initial ideas, what if this had evolved differently? What would we be doing in terms of deflection missions? How can we get there? Some groups actually started thinking about that, so it was a good test case. The exercise that Lorien already mentioned was something that was going on in parallel, where we had a case where we prepared for the Planetary Defense Conference. So these two things together really give me now a good feeling that in case this happens again, that we know what we will be doing.
Okay, so, well, you're mentioning the Planetary Defense Conference, that is kind of a biannual drill exercise on asteroid arrival. And Lorien was mentioning the exercise that went, well, this year in Cape Town. We did the All Planetary Defense. Cranfield University was there as well. Yes, I was there. I was talking about how Apophis, which is another close approach of a big near-Earth asteroid, will deflect some debris, which we should care about. But the thing is, with that exercise, it is again the same practice of the same page start, meeting again, and IO1 starts studying what can be done and so on. So for this year, it was particular because there was a real asteroid, and meanwhile there was the asteroid exercise as well. They were both going on together. So from these two, from the exercise and from the real case, what have you learned and what could be done better?
Yeah, many things, of course, we learned. The agencies took this whole activity, this exercise and the real thing, of course, also as a way to inform internally different groups. For an agency, for example, it's easy, as we said before, it's easy to find somebody who can compute orbits. But to find out who actually has the authority to tell somebody on the outside that there might be a potential risk, that's a different story. So typically within an agency, you need to suddenly have the mission analysis people, those that design missions, start talking and giving information to the legal people or to the external affairs department. And I think that was what we really improved a lot during these last months, that at least in some of the agencies, the cooperation between the different partners became much better. So it's not only a technical thing, you said this earlier, and the challenge is to get the political part right, to get the right people talking to each other. Now, the next step is, of course, and we started this at the Planetary Defense Conference, to inform the real decision makers and go the step beyond the exercise and say, okay, we want people from ministries and real decision makers also as part of this exercise. So we're getting there. We started this year.
Well, for what I learned from the conference, it was that it really will depend on where the impact is forecasted to be. So every population on Earth might have a different reaction. So to really get involved a larger part of the, not only decision maker, but also who can distribute the information. That is gonna be key. And I think that was part of the lesson learned. Anything else that you think you will be doing better, or you will be trying practicing?
Well, we'll be doing everything better. It's always like that. But on the other hand, I think we already did quite well.
Yes, well, I've seen it improving quite a lot since last year. So I think I've missed 1 or 2, and then it's radically changed. Now it's really a drill exercise. So that is the thing that surprised me the most. So I can totally see that we have grown quite a lot as planetary defenders.
A very modest appraisal there from Detlef. But Detlef, you're being very modest. I think you're contributing quite something now.
And so this is really a global effort, right?
It's international. I mean, in the Space Mission Planning Advisory Group, we now have 19 space agencies and offices from all over the planet, from the Americas, from Asia, from Europe. So yes, it's very international. And of course, also the UK is part of it. So that's important for today's meeting.
Okay, well, that's something that even Marco Micheli before was stressing, and even Federica from the Minor Planet Center was stressing. It is really a planetary defense. It's in the interest of everyone, and we are all part of it. So it's really something we have to take in mind. Well, Detlef, thanks a lot for coming up this afternoon. And see you at the question and answer later.
Yeah, stick around, Detlef. Some questions coming your way.
Will do.
So the thing is, okay, now we discovered that there are agencies that take part of the SMPAG and IO1. We have seen that globally everyone is really kind of involved. What we want to see is what is UK doing about it. So we can ask that to Edward Baker. Edward, you are the boss of the Planetary Defense Office, isn't it? Sounds whoa, important.
Yeah, I like to think so, yes.
Well, okay, so what is your role and what is UK doing?
Sure. So my role is Program and Planetary Defense Lead at the National Space Operations Centre, or NSPOC. NSPOC is made up of staff from UK Space Agency and Space Command on the military side, as well as in partnership with the Met Office. Could someone bring up my slides?
Thank you.
Yes, I'm just going to do a quick walkthrough of the UK Planetary Defence alert capability. If I can have the next slide, please. So, in brief, the purpose of NSPOC is to develop and operate the UK's space surveillance and protection capabilities. This is all about knowing what's going on in space and protecting UK assets, mostly satellites, as well as on Earth infrastructure as well. So, back up the next slide, please. So NSPOC operates around a dozen mission sets, but I've highlighted a few of the major ones here, including uncontrolled re-entry warning, in-space collision avoidance, severe space weather, and the reason why we're all here today, planetary defense, which is the newest service or mission set, which we established in October 2024. Next slide. Yeah, thank you. So how does NSPOC monitor asteroids? I think one of the great things about the planetary defense community is data is all open, is open for everyone. I think Detlef highlighted this as well. And we draw on this data to report on the number of close approach asteroids, including those which are deemed potentially hazardous. We look at the future asteroid risks, but the top 3, as well as summarizing the number of alerts issued by NSPOC, which so far has only been one, 2024 YR4, which I'll come on to our response to that later. We also look at the average miss distance these asteroids have with Earth, the number of asteroids discovered per month, and the customers for this. So this is part of a dashboard which summarizes, again, which goes through all the NSPOC mission sets, and it's circulated amongst UK government, space sector, and academia. So there's an awareness of what's going on in the space domain, including in planetary defense. Also, our main customers being government. I can come on to a little bit more about that later. But can I have the next slide, please? So broadly, how does the UK approach planetary defence? So we offer funding and or just general support to ESA through the ESA Space Safety Programme. We don't invest too heavily on the planetary defence side, but we've also offered support to NASA, both via the Minor Planet Centre with some of the data we've uploaded through some of our collaborative partners who operate optical telescopes in the UK, and also some of the tabletop exercise that NASA coordinated with the Federal Emergency Management Agency in April 2024. And lastly, through the thank you. And last through the United Nations, so through the SMPAG and IWAN, NSPOC is the head of the UK delegation for both of these organisations, and we represent the UK at the meetings that take place about twice a year. And the returns we get from this is the data which supports the national warning capability, as well as the data that supports our dashboard, as well as additional UK returns, which we see as investments into the UK academic and industry sector. I can have the next slide, please. So when does the UK issue an asteroid alert? We have two types of reporting. One for awareness. This is just a report type, which basically, it says it is what it says. It's to give awareness to our customers who receive these reports within government. And this is for asteroids which either have a very close approach with the Earth within the geobelt, the geosynchronous belt of satellites, which is around 36,000 kilometers in altitude, as well as potential Earth impacting asteroids, which wouldn't affect UK mainland or overseas territories. So if the UK falls outside the entry or impact path. The second reporting type is warning, where we would expect some sort of action to take place. Exactly what that action is, we don't make that recommendation. We simply relay what the effects would be, the likelihood, etc. For this reporting type, the asteroid has to potentially impact UK mainland or UK overseas territories, or have global consequences, which we broadly define as over 100 meters and over 1% impact probability. And in terms of who received these warnings, I mentioned that the recipients of our dashboard, it does slightly differ with our warning reports. The main customer for this is UK government, and within UK government, we are most concerned with telling the decision makers. And I think that's a term that's been kind of thrown around quite a lot today, and we see that as so the main one being the Cabinet Office briefing rooms, or COBRA, based in the Cabinet Office. They coordinate and control the civil responses to civil contingency threats, such as any sort of like major risk that affects the UK, whether it be natural or human-made. And we also inform the civil contingency leads for the devolved administrations, so for Scotland, Wales and Northern Ireland, as well as the Foreign and Commonwealth Development Office for any asteroids that could affect any of the UK overseas territories. I can have the next slide, please. And kind of putting theory into practice was our response to 2024 YR4. So we had only been a member of IWAN for, I think, 2 days before the global alert for IWAN was sent out. So it was good timing on our part in terms of joining. We've already established YR4 was discovered on Christmas Day 2024 and quickly identified as a potential impact threat. When NSPOC was notified via IWAN and NASA on January 28th, we immediately implemented our planetary defense alert capability. So thinking back to the previous slides, we told all the relevant partners within UK government, ensured that they knew what the effects would be, what the likelihood was. We also undertook some work with ESA to establish whether YR4 would impact or have an effect on the overseas territory of the Ascension Island. If you do look at the entry path or potential entry path for YR4, you can see it. We could see it pass quite closely to the Ascension Island, so we were able to quickly establish and relay to the Foreign Office that there wasn't actually no risk to the Ascension Island, which was again a real good demonstration of the UK's capability and the importance of having NSPOC as the sort of the recipient and distributor of these alerts and coordinating that UK effort. Other activities we took during the sort of response to YR4 was representing the UK at the meetings of I1 and SMPAG, which took place in Vienna, as well as leading on social media and news media public requests and publicizing updates. And luckily, as we all know, YR4 was deemed a near zero impact threat, which is good. There still exists a 4.3% chance of impacting the moon in 2032, to which I don't believe any international protocols or procedures exist. So interesting to see how that develops. But that's just a summary of our response to YR4. If I go to the next slide. So if you'd like to learn more about NSPOC, just please visit the website. We publish monthly stats on what's going on in the space domain and what the UK is doing, including on planetary defence. We've published one blog already on our planetary defence capability, and we're publishing another one either today or tomorrow on our response to YR4, celebrating Asteroid Day. That's kind of a broad summary of the UK's activities. So it's varied, but it's also quite new. NSPOC was established in May 2024, so it's still kind of getting set up. But I think it's a good demonstration of what I think individual countries can do nationally and contributing to the multinational response which is required for planetary defence.
Yeah. Well, have you got a way to already establish to disseminate the information to the public, or your role is just to advise the government at the moment, and then they will decide how to disseminate in case of impacts or anything you have to say to the population, to the UK population, obviously?
Yes, primarily it is to government, but we also, I mean, I think with this data, as kind of has been established, it is more public, so the general public can see it, do see it. It's written up in newspapers, which they do see. I think our role in government is just to provide the government response to that, which I think in the case of the asteroid risk is to not let it get too sensationalized, to try and offer, this isn't in most cases something to really worry about. It's just something to be aware of and to reassure that a proportional response is taking place. So it's really just keeping up with the narrative that's in the public domain and making it known that the government is aware and is doing something about it.
Okay, well, thanks very much. That was very interesting. It was a kind of zoom in after we have seen the whole information getting global and global. Then obviously, if it comes up to a single place, then we have to understand how the mechanism will go local again, back to local. So that was very interesting. We can call back our guests for the question and answer
There's
first.
a few questions. It was just nice to see Edward there. There's been an Italian basis to pretty much everything we've heard about so far today, and the UK thing. Yay! Let's hear it for the UK. It's more than nationalism. There's a real question, technical question here from Matt. I'm not sure who to put this one to, so I'll put it out there. What is the arc length needed for a good orbit determination result?
I think.
Do you want to start?
Yeah, I think I might go for that. So the thing is, the arc length is, well, what is the time between the first observation and the last observation of it. So it gets better if the observation is the longer time possible. So at the very beginning, you've got kind of the first 3 observations are taken in 3 different nights to call it an asteroid. So that is already enough to have an orbit determination. A preliminary orbit, and so I would say 3 nights pretty much. Well, the imminent impactor are even less than that, so you observe it and they're gonna impact in a few hours, so you have to shrink that. But the traditional techniques will go for 3 nights observation, and then you have got the orbit determined, even badly, but then it gets better when the arc gets longer. So 3 nights minimum, or if it's shorter, then you have to go through the imminent impactor, or at least to a trigger that is, well, a different mathematics to determine the orbit, something like that.
There's no more questions in the chat in terms of YouTube. If you've not had a chance to put a question into the chat, please do that. If you've gotten this far in the recording, congratulations, well done. Please get in touch. if someone has an interest, who do they get in touch with? Is it you? Is it any member that we've seen on the panel today?
Well, in Cranfield, we are studying asteroids and orbital dynamics quite a lot. So I would say if you have the chance to, attend the courses, then go for it. There are plenty of events throughout the year. And then, everyone that was on today is always busy with events or with some divulgation experience and so on. You can contact any one of the Avengers that we had today, definitely. I have a question for our
guest. Please, go ahead.
So how do we know you're not hiding something? Is something going to impact?
Paranoid talk, that is. Who are you putting that to?
Well, I don't know. Whoever wants to reply that, probably, I don't know. Detlef, is he the coordination part of the recommendation?
The question about hiding something in the modern times of internet and very capable amateur people is mute, because we cannot. I remember a long time ago, people were thinking about this impact corridor, i.e. where on the ground would an asteroid end up if it were to hit. And we decided, if you have like 1% impact probability, it doesn't really hit the Earth anyway, so we didn't publish anything. But a day later, there was a Wikipedia page up there by somebody who computed this. So I think it's very difficult to hide things in our topic, because the asteroids are out there, they are in the sky. There are amateur astronomers that have, in the meantime, rather large telescopes, good techniques, and many people follow what we are doing. So I think we are under constant peer review here. And that's why it would be, in my view, impossible to hide something like that.
I've got a question for Ed, following on from Detlef, what you just said there. What then is, Ed, to you, what is an expert? And not so much who's an expert, what is an expert? As Detlef said, we're all able to do this sort of stuff. Ed, what do you reckon?
As in who in...
Do you need a degree in astrophysics? Do you need a degree in asteroids? I mean, what counts as an expert?
Oh, well, I'm not entirely sure. I mean, I'm certainly not an expert in the sense of having academic qualifications in asteroids. I think with the with planetary defense, it requires a broad church of expertise, not just in physics or engineering, but also in disaster management and resilience and experience within government. So I'm not entirely sure. Sorry, in terms of what exact expertise is, or who the expert, what an expert is in this domain.
Thanks for being honest, Marta. I'm going to put that question to you. Do you see yourself as an expert?
Well, I've been working at the Neo Coordination Center for a while, and I know my part, as Edward was stressing. Everyone has got a different expertise. So I'm a mathematician as a basic, so I know something about orbital dynamics. I don't know much about neither observation nor the, not even the communication, definitely not, and everything else. So
it's truly collaborative.
Yes, it has to be. It has to be collaborative, because it is the only. If you are a scientist, but not only, you know very well how to do your bit. The important thing is to keep coordinating with everyone else. And I think that even SMPAG, the work is doing, is to take information not only from the scientists, not only for observers or impact monitoring stuff, but also from agencies that can say, well, you know what, to tell the population about this danger, we need this amount of time. And then they take the information from the office, like Lorien office, for what is the tsunami probability, and then they must know a little bit of that. So everyone knows their little bit, but it gets all together, and that's extraordinary for the planetary defense.
And Lorien, can I ask you a question? Should we be worried?
So this is a field that is high consequence, low probability events is what we're looking for. So the chance of a very large asteroid, striking Earth get lower and lower the bigger sizes you get, because there are fewer larger asteroids out there than there are smaller asteroids. But it is also, one of the hazards that we can prevent if we know it's coming. So it's important to prepare for those low probability events, because the potential consequences could be high and because we could do something to prevent them. So I would say, no, we don't need to be worried on a day-to-day basis. A lot of the ones that would be substantially large, we would hopefully be able to detect in advance, or we already know they're out there and are tracking them. So this is not something that, you know, people need to worry about as a likely event in their life. But it's something that it's really important that we're all prepared, that we know how to handle when it comes our way.
There's another question, Ed, this one's to you from Francesca. Francesca's asking, what can be done to secure more funding for planetary defense in the UK? Is it a change to the risk list? Is it changes to the risk list needed? Ed, to you.
It's a complicated answer. I think, you know, what we have to be aware of is asteroids planetary defense is one of many hazards in the space domain, which we have to sort of consider our response to, both on a national and multinational basis. I think, you know, and as well in the UK, in the tight spending environment in which we operate, in terms of exactly, you know, how more funding would be achieved, I'm not entirely sure. I think the work we've done in SMPAG and within the UK over the past year on the government side has certainly helped to raise the profile of planetary defense. I really see my role just to relay the importances, to make sure that decision makers as well as politicians have all the information they require to make those decisions, because I'm not close to many other risks in the space domain and other risks that face the UK, both natural hazards or human-made ones. So I think the importance for me, and I think the community as well, is just to highlight exactly what the risk is. And I think Lorien highlighted that really well, summarized that really well, saying, you know, this is a high consequence, low probability event, and it's just making sure that that's known, and that it's known amongst all the other risks which we need to respond to. And once those decision makers have all that information, if it's deemed that more investment into planetary defense is required, then that's what we'll do. I think the great thing that I've done over the past year in setting up this alert capability, joining I1, we also co-sponsored the UN resolution to make 2029 the International Year of Asteroid Awareness and Planetary Defense. That was all relatively low cost. So if there are other blind spots, gaps in the capabilities which we need to fill, when there's a credible reason for us to do so, then I believe we will. But the exact pathway to which we achieve that, I'm not entirely sure.
Is it true that asteroids are not in the risk list of the government, of the UK government, obviously?
Yeah, that is true. I can just give a quick summary for the audience exactly what that means. So the UK government, so the Cabinet Office, which I briefly mentioned before, operates a living document called the National Security Risk Assessment, or NSRA. And that is the government's principal tool for identifying, assessing, and comparing the most serious risks facing the UK. It doesn't aim to capture every risk that the UK could face, but instead what it aims to do is identify a range of risks that are representative of the risk landscape, and can serve as a cause agnostic basis for planning for common consequences of those risks. The National Risk Register is the external version of the NSRA, and it can actually be found on gov.uk, so you can go and give it a read yourself. And risks in the NSRA, the National Risk Register, are all based on what's called a reasonable worst case scenario. These scenarios aren't predictions of what is most likely to happen. Instead, they represent the worst plausible manifestation of that particular risk, once highly unlikely variations have been discounted. And so asteroids aren't currently on the National Risk Register. There was a review of it between 2019 and 2021, and from what I gathered is that asteroids didn't meet the criteria on the likelihood side, so they weren't deemed to have to happen frequently enough to be included on there. But it was also noted that we've spoken about some of the effects we would expect from an asteroid impact on Earth. Many of those effects are already covered by other risks in the NSRA. So a big part of the work that I've tried to do when I've been speaking about planetary defense is to highlight that whilst the risk doesn't appear on the NSRA, if we were faced with a potential asteroid impact on Earth, many of the effects we could see are already well covered. So again, that kind of plays back to what I was saying before. The most important thing, at least in this initial period for the UK, is to ensure that if there is a risk, relevant people within UK government know about it. They know about it quickly, effectively, and they know about it from a designated UK point of contact, which is NSPOC, National Space Operations Centre.
Okay.
Any more questions for the panel? You seem engaged there. There's nothing else from the chat other than some answers to the game.
Oh, then we have to definitely. Well, first of all, let's thank our guests of today. So thanks again, the 4 Avengers of the second part and also the first part. Thank you all for spending the afternoon with us, and thank you for for the work you're doing. Fantastic job.
Thanks, guys.
So I hope you've learned something about asteroids in the afternoon. So you mentioned that there are some solutions.
There are. Well, there's a kind of a spread bet going on there. Kimon has had 3 guesses. And I think there's an answer in there. H2, H6 and E3.
H2, very well done.
Very good.
H6 you were mentioning, and then what was the third one?
E3.
E3.
No.
Let's see it. So the first one that we have.
Hang on, there's another one.
Oh,
Elisa has H2 and H6.
Those are both correct. We can see them right now. So 1998 HQ7, the arrow is pointing in the direction. You can see it moving in the, you can see the moving dot.
Just about see it, yes.
Yes. So the second one is 2015 GT43. The year is actually the year in which they were discovered. The letters and the number will tell you about the month and which asteroid of the month it was. So that is the second guy. And then we have the third one, which is teeny tiny year. You might even not be able to see it with the, that is why I've added this more. So you can see it first arrow, second arrow, third arrow, fourth arrow. Now, like 1, 2, 3, 4.
Gosh, Marco was saying it's easy with the naked eye, but I can't see
this
that.
Is exactly what Marco is doing all day long. So searching for asteroids, and
Incredible.
yeah, you need a closer look. But those are the actual 4 spots of it. So this is the solution of the game. Thanks to everyone that took part
Kimon
of it.
and Elisa, well done. You got the
Yes.
you got the correct answer. Brilliant. Thank you so much. We have finished.
Yes.
Gosh, it's gone so quickly. I've learned so much about asteroids that we shouldn't be worried. I took that away.
Yes,
Let's
definitely
not worry
not.
too much, and then nothing has been hidden either.
Yeah, no, nothing. Definitely not. It's, well, as Detlef was saying, it's definitely impossible to hide something. Yes.
Wow.
So, well, I hope you enjoyed the day.
It's been
Thanks very
fantastic.
much for hosting me, and see you maybe at the next Asteroid Day.
Who knows when that's going to be, but maybe the Perseus we're going to do something. Thank you for watching. It's been fantastic fun. If you've gotten this far in the recording, congratulations. You deserve a pat on the back. Get in touch with anyone that you've seen on the screen if you want to find out more. So Marta, thank you so much. The studio managers today were Chris Ripley and Marta. Thank you again. The producer was Marta. So thank you for watching. My name is Toby Thompson. Thank you for watching.